A value is what I like to call the initial value. Some people call it the starting value. So when we're doing like a population model, for instance, it would be the initial population of something. What it is on the graph is the y-intercept. The B is the numbers are being multiplied by. An exponent means repeated multiplication, and so we call it the growth or the decay factor. So when you're multiplying numbers, what makes the numbers get bigger if what you're multiplying by it is what kind of number? Should be positive, but what, like 0.5 is positive. If I multiplied by 0.5, would that make numbers bigger? Bigger than 1. Okay, so for this growth decay factor, what we're going to say is if B is a number that's bigger than 1, that is growth. That's exponential growth. And if B is a number, we're not going to say less than 1. What we're going to say is it's got to be positive, so between 0 and 1. That's what we call decay. And just a reminder, what's anything to the 0 power? 1, okay? That's why this is the y-intercept, because if I would put 0 in for x, b to the 0 is 1, and I'd be left with a, so I have the point 0, a. I think you guys probably know this, but a picture of growth, if I wanted to do a picture of growth, looks like this. And if I wanted to do a picture of decay, it's a decreasing function. Without transformations, meaning if I don't bump it up or down, there is a asymptote. Do you see it? It's a horizontal asymptote at y equals 0. Yeah. Good. All right. So let's just review a couple rules, like I was talking about on the board. So if I asked you to evaluate 3 times 5 to the x power, first of all, if I were to graph this, would this be exponential growth or decay? Growth. So the y-intercept would be 3, and then I'd be multiplying my points by 5 to find more points. Let's find that when x equals 2, and we're going to just practice doing some of that multiplication. I know it's kind of early. All right, so that would mean what? 3 times 5 squared, which is 3 times 25, which is 75. Okay, so that's how we evaluate them. Let's try a different one. When x equals -2, I'd like you to understand what that means, okay? And obviously, could you use your calculator if we start getting really large powers that you don't know in your head? Yes, but I want you to understand that this really means that I'm going to take 3 times 1 over 5 squared. A negative exponent means we take the reciprocal. And so really this would be 3 times 1 over 25, and I just leave it as a fraction, 3 over 25. Does that make sense? Let's try then one that's a little different, similar to our opener. How about let's find 3 times 1/4 to the x. So now this is decay. This is decay if I were to graph it. And then let's do, we'll do x equals 2, and then we'll do x equals negative 2, but then let's do this when x equals 1/2. Okay. All right, so when x equals 2, so when we raise a fraction to a power, you raise the numerator and the denominator to that power. But what's the numerator? 1. So 1 to any power is still 1. Okay, so this would be 3 times 1/4 squared, which is 3 times 1/16, which as a fraction is 3/16. Getting that? All right, try the second one. So this is the same as 3 times 4 squared, which is 3 times 16, which is 48. Good. Then let's move on to, we call this a rational exponent because it's a fraction. A rational number is something that can be written as a fraction. And so let's review this. If I had 3, I'm going to do it over here because I need some more room. 3 times 1/4 to the 1/2 power. What that means is 3 times the square root of 1/4. Okay. Why? It just does. What it means is what number multiplied by itself twice gives me 4. I'm going backwards. Okay, I'm reversing the second power. I'm reversing the second power. So I'm trying to go back and figure what number squared gives me 4. If it was a 1/3 root, I'm trying to go back and figure out what number cubed gives me that number. Okay, so a rational exponent reverses its reciprocal exponent. So what's the square root of 1? What's the square root of 4? So this is 3 times 1/2. Or 3/2. Okay. I'm going to do a couple, just 3 more examples for those of you who need to review rational exponents. And then if you need more practice with that, like I said, I'm not going to spend time on it in class, but you can look. I'll put a video on Google Classroom. Would you try then? Let's try these ones. If I said 25 to the 3/2 power, we'll do that one, and we'll take 27 to the 1/3 power, and then 8 to the 2/3 power. Okay. I don't have any handy. But Daryl and Jackson, I don't know if you remember, I gave you guys an Algebra 1 root cards, okay? And so what I gave them basically was a whole list of cards where it went through 5, and then I wrote what 5 squared was, 5 cubed, 5 to the 4th. So they had a handy little card to reference, okay? Don't type this in, but if you need your calculator to evaluate some of those powers, you may. Let me show you what this really means. This means 25 to the 1/2 power cubed. Okay, so when we have a rational exponent, what that means is a power to a power, we would multiply them, correct? 25 to the 1/2, we said, is the same as the square root of 25, but then we're going to cube it. So what is the square root of 25? 5. So this is the same as 5 cubed, or 125. Okay, and so that's how fraction exponents work when there's a numerator and denominator. The bottom is the root, the top is the power. Okay, this one should be easy. 27 to the 1/3, what root is that? This is the cubed root of 27. In other words, what number multiplied by itself, not times 3, but by itself 3 times, gives me 27. What is it? 3. All right, this one means 8 to the 1/3 squared. Following? So this is the cubed root of 8, then squared. What's the cubed root of 8? 2, and then 2 squared would be 4. Okay, so at least I wrote all my steps out there for something if you're a little, not remembering that from Algebra 1. All right, so let's talk about how to make a function. So I'm going to give you some table of values. And in the left column, I'm going to put x. In the next column, I'm going to put a function h of x. And then we're going to do a different function, g of x. All right, so I'm going to put the values for x as -2, -1, 0, 1, and 2. Let's do a function for h of x first. 4/9, 4/3, 4, 12, and 36. Let's find a function for h of x. All right, so here's the deal. Remember, in general, I'll write it really big at the top of the page, we have a times b to the x. Do you remember what a was? It is a number, but what would be specific? Initial. Did you say initial number? Initial value. Or it's the value of the y-intercept when x equals what? 0. So if I want to find a in my table, I'm going to go right here. So my function has an a value of 4. Do you remember how I said b was the growth or decay factor? So what I want to do is, and I got to be careful with this, I want to go forward. I got to figure out, it's not division, what it's multiplied by. Now you might have to use division to figure it out, but how do I get from here to here, and here to here, and here to here? You might not see it at first. Multiplied by 3 times by 3. And we say this in Algebra 1, we actually go back and we divide things, and we say, hey, if you get the same quotient when you go backwards and divide, this is exponential. So my function then was h of x equals 4 times 3 to the x power. And this would be growth or decay? Growth. Very good. All right. Do another one. Now we'll do g of x. I'm going to do 80. And again, we're looking at, this is when x is -2. And then this is 20, 5 over 4. That's hard to see, isn't it? This is 5 over 4. And 5 over 16. All right. Who wants to try it? G of x equals 1?
5 times 4x.
Okay, so I have a question for you, Juan. What's 80 times 4?
The 1 4.
Ah, yes. So be careful that we make sure that it's going forward. So this, you're right that there is a 4 going on, but these are divided by 4, which is the same as multiplying by 1/4. So we'd write 5 times 1/4. Typically when it's a fraction, I like to just put it in parentheses, just in case it's a fraction that's not a 1/4. Because if it's like a 2/3, then I'd have to remember to do the numerator and denominator. Does that make sense to you guys? Okay. All right. Then the last thing we should quick talk about is how we sketch graphs with transformations. So I'm going to do one example like that. Gosh, that's blurry, isn't that blurry? It's a little better. All right. If I asked you to take the function f of x equals just 3 to the x, and then we're going to graph g of x equals 3 to the negative x, and then h of x equals 2 times 3 to the x. Go back to our transformations from earlier in the year, okay? Really, if this number is a 1 times 3 to the x, so the y-intercept of this function is just 1, okay? And then I'm multiplying by 3. Do you remember what happens when I make the x negative in the function? What is that? Flips it over which? Ah, this is the y-axis. A negative out in front is the x-axis. All right, so some sketches of this graph would look like this. Doing it without our calculators. The first one, f of x, if I put in 0, would go through the point 0, 1. And let's just put in one more point. Let's put in 1. What's 3 to the first power? And so then it would also go through 1, 3, and I just draw a smooth curve. All right. 3 to the negative x would be flipped over the x-axis. No, the y-axis, sorry. This point would not change. But this point, 1, 3, would go where? Negative 1, 3. Hey, now it's not growth anymore. What is it? Decay. I'm going to go back to that in a second. So this is g of x. Reflect over y-axis. What if I put a 2 in front? I know we know that the y-intercept is now what? Instead of 1, it's now 2. But really what this means in transformations is this is a vertical stretch of 2. So this 0, 1 would go up to 0, 2. And the point 1, 3, multiply the y-coordinate by 2. What do we get? 1, 6. So 3, 4, 5, 6. Okay, so that's just a little bit of some sketching graphs and how they're related to a basic function.